The sun's having its main character moment. But what's really going on behind all that summer shine? SSAI senior scientist Serguei Martchenko breaks down his journey to SSAI and how solar variability isn't just space talk. It's key to understanding how our star shapes Earth's atmosphere and your everyday weather. Let's dive into the science behind the sunshine.
I was born in the Soviet Union. Interesting, right? Yeah, dysfunctional Soviet Union, Ukraine. Then I earned my PhD from Estonia, part of the Soviet Union. And that was the PhD in astrophysics. Astrophysics. So I'm an astrophysicist. It's a passion of my life. I actually keep publishing in that area a little bit for the fun of it, right? Then at some point, I was invited to go as a first postdoc. Wow, first postdoc to the Instituto de Astronomía, Ciudad de México, Distrito Federal. Por eso yo hablo español. I speak Spanish, of course. I spent 2 years as a first postdoc in Mexico. Then I remember that day when I was invited to join one of the most renowned teams of the massive star researchers in Montreal, Université de Montréal. Pour ça, je parle français un peu, mais lentement. I speak French, broken French because of that, a little bit. I came to Kentucky as a research professor, taught a few thousand students, and did research. My students are all over the United States now, pursuing careers. That's good. Good to know. Some are in contact with me. Well, then I'm with SSAI since 2008 as a research scientist, and we'll talk about the research a little bit later. So what represents me as a scientist, I published probably like 250 papers. I don't give the exact count of that, because some of them are small things, small potatoes, but I do count on about 100 plus refereed publications. These are very important milestones of the career, I would say, which collected so far about 5,000 citations, maybe not so much, not so stellar, but at least some of them were recognized. And of course, I work as a big part of the international collaboration. And we'll talk about later, basically, a little bit about the projects. So, wow, that's a loaded question. So one question in two, the sun and the NO₂ trace gas, let's call them trace gases. This is the two major projects I basically pursued working with SSAI team and NASA team. So let's split those couple of into two parts, the sun and the NO₂ parts. And I'll try to connect them basically the best I can because they're connected. So let's start from the sun. It's my favorite subject because there is so much to do, and it's really interesting thing that we live by this hot furnace for the past 4.5 billion years, and we know so little about that, how it works. We know enough to go by, but this enough is not enough, actually, as it turns out. We don't know enough, and then I'll explain why later on. Okay, fine. So what is the sun and why we basically study it? Of course, the first point I would like to make, it's a very obvious one, actually. The sun is our energy. To be back to the numbers, the important numbers is to say that the sun delivers 99.97% of the energy into the Earth atmosphere and the Earth ecological system. So it's completely dominating energy intake. How that energy processed, that's a different question. I'm not touching that because it's a very complex process. But let's talk about this total input, complete domination. And what that domination means, that we live by the sun and we depend on the sun intimately. Practically all our food coming from the sun energy, if you think about it. Without the sun, there is no food within the Fuchs. That's it. No crops, no animals, no nothing. no microbial forms, which are feeding on us and we're feeding on them. Okay, fine. But second point, sun is the very important source of energy, dominating source of energy. Second point, it's not only this total which matters, it's how this total is distributed over the spectral domain. I'll give you a couple of examples. For example, you take a look at the sunshine, you can perceive it, you can see it, right? It's a visible light. And this sunshine controls the heating rates of the surface, the cloud formation rates because of the heat and so on. And basically, this is visible light. Okay, let's move to the light which cannot be perceived by our eyes. UV, for example, ultraviolet, really short wavelength stuff. We can perceive it, but it gives us the nasty sunburn at the beach. And moreover, it completely controls the chemistry of the upper troposphere and stratosphere and the energy balance there, and the chemistry influences us and so on. So my point here is that we really need to know how that energy is distributed across the spectrum. Okay, fine. And this is a tough point, actually. If we talk about the total output from the sun, we learned over the past, like probably 40, 42 years, intimately learned how to very precisely characterize the total. We are able to measure the total at every practically second of the sun, delivering the total with an astonishing accuracy and precision. Those terms are interrelated, but they are not the same. So that precision is coming at the 5th or 6th decimal point. That means that we measure the output from the sun every second, practically every second, with a few parts, let's say 5 parts per million precision. It's an amazing feat. And well, here we stop and say, okay, what about the spectral? How we distribute that total? We're fixed with the total. We're fine with that. Almost there. We need that accuracy and precision, and we can measure it very accurately and precisely. But what about the spectral distribution? Here, this is where I work. And here we are going through the crunch. Because over the past 20 years, we learned how to measure that spectral distribution with a precision of 0.1% or so. But it's still about 10 times below what we need. So we are kind of midway, but that midway, the lower you go, the tougher it gets. So if we breached the first order of magnitude precision within the 20 years, I'm working in this field for the past 10 years, and then we haven't done much of the shaving off of the errors and so on in 10 years. It's a very tough problem. But nevertheless, I mean, the science is about trying, being very stubborn, being very persistent, and basically trying and trying and trying until you fail and until you're done with and say, I can't take it anymore. But we can take it, and we're trying. So the spectral stuff is very tough. Okay. And we're not there yet. And that's where I work. And then what we realized that actually, hey, can we do something about it? When I say we, it's mostly Matt DeLand, SSAI, and I. We just thought it over at some point. I met Matt a long time ago and then started working with him. And at some point I said, Matt, why don't we try that? And Matt said, oh, I tried. And it didn't go far. And we rethought it. And we thought it again because Matt was doing much earlier than me this business with the solar spectral things. And I basically joined him, and we realized that, okay, OMI, this is what you asked me about in your question. OMI is the Ozone monitoring instrument. It's a Dutch-Finnish instrument flying on a NASA spacecraft, or beautiful sense of the scientific legacy. It's one of the best instruments NASA launched in an Earth observing conglomerate constellation. So OMI is part of that. It was built in Europe, and so we work with the colleagues across the ocean closely on the issues. It's an international team, broad collaboration, many years spent doing the business together, and it's very fruitful business. So enters OMI into the landscape of the solar physics. OMI was meant initially, never meant to be a solar instrument. Nobody thought about that. And Matt said, okay, why not? And I said, why not, Matt? Let's go for it. And we went. And we turned it into the solar instrument at some point. That's a funny part of science. You can do something nobody, and then that's the funniest part of science. You can do something nobody thought of. And if you're persistent and clever enough, you can do it. And that's amazingly rewarding, actually, notion that nobody thought about it. No matter how stupid it sounds, let me try. And it was stupidly sounded idea from the beginning, but then we spent about 5-7 years trying and failing, going back and forth. And finally, OMI comes up as the good solar instrument. Why it's good? Because it's flying since 2004. It's a very long-lasting mission, and it's still flying. And this is essential to fly very long time to capture the solar cycles. The solar cycles are, let's say, on average about 11 years old. So OMI is almost 2 solar cycles, flying almost 2 solar cycles. It's going through almost 2 solar cycles. It makes it unique. No instrument did it. Very few instruments, actually, not no instruments, but very few instruments did it. And it's a very stable instrument. And this instrument resolves the solar spectrum. So it gives you the broad enough range to exploit it for the benefits of solar physics. Long-lasting, stable, predictable instrument. We spend a long time trying to predict the best we can the performance of the instrument, because it's a very important thing, how the instrument behaves in time. So we solved those problems to some extent. The problems keep creeping in. They're heartbreaking sometimes, and you spend month and month doing some very tedious job to eliminate the causes of instrument drift and so on. But nevertheless, I think to some extent, we established a pretty good benchmark. So people started using the OMI data for the model validation, major model validation, model development, and so on. And we're working with a broad international collaboration now of the solar model people. And we're contributing the data from the instrument, which never meant to be that. So second thing about OMI is that actually OMI is able to see, not clearly enough, but to see, like it's bad glasses kind of the seeing, but nevertheless see some important features in the spectrum. We call them Fraunhofer lines. German physicist Fraunhofer lines. It's a solar lines absorptions coming from different chemical elements, mostly hydrogen, then helium, and so on, metals, iron, and so on. So what those lines are telling us, they're telling us about how the sun works. And this is the unique part of OMI, and we keep publishing lengthy, pretty well-cited papers about that. I'm not going about the results. I'm not describing the results because I don't understand those results myself sometimes, because they are perpendicular to what we expect. Sun is not doing some things what we expect from that sun doing. And okay, fine, it's not about the results. It's about why do we need to know how it works? This is what I mentioned to you earlier. And this is the important thing, how it works. We try to understand how it works and why. Why in heavens we need that? We have enough food, right? Why do we need to understand how it works? And my answer is simple: money. Could you believe that? Fundamental science about the sun is making good money. Why and how? Okay, fine. Let me quote you a couple of things. The first one is that by prepping up for the interview, I thought about what I'm going to talk about. And then, of course, I just checked the websites, a couple of websites. And then to my astonishment, I never thought that I will go that high. And I read that high the numbers. I learned that in year 2024, the total revenue from the commercial satellites revenue was around 293 or 296 billion a year. That means, what means the revenue? All the telecommunications, all the geolocations, all the timing, all the positioning, all the Earth mapping comes as a revenue. You see the broadcasts from the satellites, that's the revenue. Okay, fine. Money. Okay, let me give one more money example. And then if you go forward, and then I read a couple of reports, and one of the reports, it's not, I think it's a little bit optimistic, overly optimistic, but it says in 10 years from now, the total commercial satellite industry, it's called a space economy, will have the total value of $1.6 trillion. Because now, in 2023, it was valued at almost $700 billion. We talked about the revenue, now we're talking about the total volume of the things. That means the hardware, the products, the revenues, whatever, whatnot. Okay, fine. Let's put even $300 billion to the table and ask the question, why do we need to know how it works, the sun? Simply put, the solar flare can wipe out good percentage of that hardware in space in a matter of few minutes, fry the electronics. So your $300 million are not decimated completely, but gone in good proportion in a matter of few minutes if you don't know how it works. And we do know to some extent, but not enough to rely completely on that knowledge. So we need to expand that knowledge. That's what we're doing. We're going deep and trying to dig up how it works, things for the industry to go up and meet the final frontier, quote in the Star Trek, yes, the space, to meet the space and be successful in space. Basically, this is how the fundamental science links to the very needy space exploration events going around the Earth orbit. So we need the models, we need the predictions, we need the safety coming from the models because of the predictions, precise predictions, predicting. And for that, we need the data. And OMI is supplying the data, basically. I'm trying to simplify it because, to be honest with you, some of the concepts, they go perpendicular to our expectations, and I'm still digesting those things. And then I don't want to, to go and put them on a table because there's a lot to think of. We are revising some things as we speak, our understanding how it works in this domain. Okay, fine. So let's go to the second subject. And actually, I'll try to link the first subject, the sun, to the second subject, the trace gases, our atmosphere, our Earth atmosphere, by saying one thing. And this is a very simple thing. We use the very same sun to calibrate the OMI instrument and go to the main mission of the OMI to observe the trace gases. Ozone monitoring instrument means that ozone is the main constituent trace gas of the atmosphere. Why do we call them trace gases? Because they measure it in parts of million or billion. So they're tiny, minute things, which you would say, why bother about those tiny, minute things? Because the rest of the nitrogen, oxygen, a little bit of the CO2, and the rest is minute, tiny. Actually, those minute, tiny things, I'm sorry to say, but I'm quoting one of the websites I provided you with, is linking to the publications, and those publications say those tiny, minute trace gases, some of them, not all, but some of them, cause 8 million of the premature death worldwide in a year. think about it. Premature death, that means that people with asthma, people with bronchitis, chronic bronchitis issues, with breathing issues, with the tract issues, lungs, and so on, people with allergies, severe allergies, are cut by those trace gases mercilessly, especially ozone. NO₂, my favorite, which I spent probably like almost 15 years working on different aspects of NO₂ gas, trace gas, one atom of nitrogen attached to two atoms of oxygen, NO₂, simple stuff. But that NO₂ is the precursor of the really bad guy, ozone. You may have heard about the ozone, high levels of ozone. And you may have heard, I mentioned that I spent a couple of years in Mexico, right? And actually, that's how I learned about ozone. Look, the life is a funny thing. It's tea and curvy. And then I learned about the bad ozone problem in Mexico City when the ozone levels exceeded the critical, unhealthy levels. There is a threshold. Unhealthy, it's yet healthy here and unhealthy there. So every month over the winter time, the critical levels in Mexico City went 5 times above the threshold. And what you experience when you're sitting in the office, that your eyes, they start burning, the throat is like going through the bad cold after the couple of hours of the exposure. And this is ozone. This is really immediately recognized as the bad one. And the NO₂ is frequently preceding that ozone and helping it to form around. So I'm about NO₂. I'm not doing ozone, though I did some ozone work, but not that much as on NO₂. Both are trace gases. Both are minute, but they harm you a lot. So let me introduce to the NO₂. Problem, and it's not a problem, it's just how it is. NO₂ is formed naturally in a stratosphere. You remember I mentioned the UV reactions, ultraviolet light, and that's how it formed. That's the high energetic energy light, which triggers all the reactions. So the ozone and the NO₂, they're reacting on that sunlight coming in. That's how the sun comes. Fine. So if it's in stratosphere, like 10 miles up, who cares, right? But what is interesting, this is the natural pathway for the NO₂, but there is an anthropogenic pathway. Us, the humans, doing the business on an Earth surface, and that business basically is about the combustion, meaning that's the power plants, the cars, the trucks, the big fires, that Canadian fire, and the smoke and the bad things today. Sunny, beautiful day, but you better stay indoors because of that smoke coming. This is the doings, partial doings of the NO₂. NO₂ from the Canadian fires cannot reach us, but it triggers the formation of the aerosols, the haze. The haze is all over, and we breathe that haze. So this is NO₂, and this is the things done by us to pollute with NO₂. Okay, fine. So NO₂ is pollutant, not the most harmful, but nevertheless, it's a pollutant which leads to the more harm done ozone. And we need the monitoring. And here comes the OMI. I mean, you see the synergy of the things. OMI can deliver both ways, for the sun and for the Earth atmosphere. And this synergy leads to the OMI is the main instrument which is monitoring the NO₂ trace gas worldwide. It can put together the maps in about 2 to 3 days, worldwide maps, and see where that NO₂ is produced, at what rates it is produced, how it is transported. It's a short-living gas with long consequences because it triggers the chain of the reactions which leads to the different pollutants. So we map, we see how much it's produced. What are the sources? Is it the transport? Is it the power plants? And so on. If it's a transport, what can we do about it? What can we do about it? It's very interesting and pertinent question, actually. What can we do something about it? Yes, we can. And at some point, we learned doing those global monitoring maps, we learned that actually our products are more and more accessed by the local governments, not only at the federal level, but even at the state level or county levels. They need those products to basically to think long term, especially at the federal level and state level, to think long term, to think twice, should I put that power plant here when it's completely dominated by the local winds, so it will produce the huge red blob on our maps, high contamination from the NO₂ burned by that plant. Should I put the scrubbers, extra scrubbers in that plant? If it's the only place to put that power plant, should I put the extra scrubbers? That's how they learn about the NO₂, and then it's more and more accessed at this level, which is really pleasing to see that the fundamental stuff we're doing, it's slowly propagating. It's a tedious process. You need to learn to interpret, how to interpret those things, how to learn about the impacts and so on. And we're helping to learn this way. But first of all, it comes from this very simple step. You need to produce the data first and then find the user. And we find the user. Unexpectedly, the demand for the data is slowly creeping up over the years. At the local levels, even the counties sometimes are interested in those maps. So that's what we do, trace gases, the sun, and then we continue expanding, of course, working with different people, with different universities, different institutions in Europe. We expand this effort. Now there is a next generation of satellites, new generation of the satellites coming up. Those are beasts, real beasts. In comparison to what we do with OMI, the data rate is about 100 times, sometimes 1,000 times higher. We're drinking from the fire hose, yeah, literally. I mean, it's a staggering amount of the data, so we need innovative things to process that data cubes. And it's not coming easy. There are so many tricks to learn. And this is exciting in a way that we can learn so much more, and there are machines working for that. But the pitfall is that we can't quite, it's like working with the sun. I'm satisfied sometimes to process 1% of the data, but you need to carefully choose those data, because I cannot imagine processing 100% of the data. It's that amount of the data. We are facing this dilemma in the Earth observing now, but it's exciting, basically. Okay, sun, personality. All right, fine. Middle-aged, grumbling, ambling, ponderous, deity or demigod or semi-god, detached, aloof. You may call it aloof. Why? Because basically, if you ask that big entity the question like that, like you're asking the reaction to the solstice, I would imagine it answering, who are you exactly? Okay, I can barely see that third rock from the sun. If you know the show Third Rock of the Sun, one of my favorites, watch it. So if you know that show, it's the third rock of the sun. I can barely see it. And that sun is saying, I can barely see that little rock. But who are you exactly besides that rock? Humans? Huh? Never heard of. I better never hear of them. And solstice? Human solstice? Oh, my dictionary is expanding. Never heard of. And exactly why you're bothering me with this nonsense? That's a sun. That's a sun telling you the things. Mm-hmm. And the last word is find somebody else to bother. And it keeps on rumbling and ambling and doing the business as usual, because the sun is not influenced by the planets. The planets are influenced by the sun greatly, but the sun is not. And actually, to make a little bit more funny the story, there is a specifically, I'll conclude after this short story. During one of the lectures at the Western Kentucky University, one of the brightest students in the class, asked me the question, okay, fine. So I know that you're working with a MOST satellite, astrophysics. Yeah, I heard that because it was publicized widely at some point. Okay, yeah, I do work. But you are trying to do some, that's how he learned about it, because there was the briefings, CNN briefings or something like that, about the planet around the star, distant planet. And the MOST captured that planet in very detail in a sense of the special techniques applied. And he said, okay, I'm wondering if it's so close to that distant star, how come that star doesn't feel the presence of the planet? And the planet was very massive, more massive than Jupiter, our giant planet. And he says, how come that the distant star doesn't feel anything? I said, oh, wow, that's a very interesting question. Does it feel or not? And I asked that question. I was not involved in that research, but I asked the question a couple of my fellows from Harvard. We worked with a team from Harvard on the subject. And then I asked them, okay, guys, can you double check that? During some specific times, the star may react. Can you double check? They did double check on that, published the paper, no reaction. And the planet was far closer than our Earth, and the planet was 10 times more massive than Jupiter, almost a star. So when I say about that aloof, rumbling, and ambling entity, our sun, I refer to that. Who are you? I don't feel you. I don't see you. Go away kind of attitude. This is the sun.